Alright, let's do an example for polarizing angle. At what incident angle is sunlight reflected from lake plane polarized? Now, the clue here, even though there's no value given here, the clue here is from a lake, sunlight reflected from a lake. So if I draw a lake here, okay, sunlight will go to the surface of the lake and be reflected. Okay, so it's actually the interface between air and water, and we know that for air the index of refraction is 1, whereas for water the index of refraction is 1.33. so your n1 is equals to 1, your n2 is equals to 1.33, and we can, for polarization, we can use Brewster's angle, because we know that for usually for non-metallic surface, polarization will be full polarization or completely polarized. So tangent theta p is equals to n2 over n1. So put in all the values, you can find your theta p here. N2 is 1.33 divided by 1. Don't forget your tangent, and you will get 53.1. 53.1 degree Celsius. So this will be your Brewster's angle. So what will be the refraction angle? Still remember refraction? For refraction, equation will be n1 sine theta 1 is equals to n2 sine theta 2. So your n1 just now was air. The incident angle was Brewster's angle, which is 53.1. And your n2 is water. And theta 2 is what you are trying to find, or the refraction angle. So put in all the values and calculate. So sine 53.1 divided by 1.33, you will get 0.6. Don't forget your sign, shift sign, answer, and you will get 36.96 degree. So this will be the refraction angle. Now, how do we know this is completely polarized? How do I prove that this? So let's continue just now. So how do I prove that this light is completely polarized? Now, we've mentioned before that if light passes through, if light hits a non-metallic surface, usually it is completely polarized. So we've gotten the incident angle or the Brewster's angle of 53.1 degree here, and also the refraction angle of 36.9. So how do I prove that? Okay, so here just now is the Brewster's angle theta p, which is also equivalent to 53.1, and the refracted angle towards the normal is 36.9 degree. Remember, if it is completely polarized, the angle between the reflected and refracted should be 90 degree. So let's calculate this, right? So from here to here, this is the same angle. Angle of incident is equal to angle of reflected. So this will be 53.1 also. So the balance here will be 90 minus 53.1. That will be 36.9 degree. Okay, so the refracted angle is 36.9. The balance will be 90 minus 36.9. You will get 53.1 degree. So add up these two angles. The angle between reflection and refraction ray. So 36.9 plus 53.1 will give you 90 degree, which is proven that the light is completely polarized. Okay, let's try another example. The critical angle for total internal reflection at the boundary between two materials is 55 degree. Calculate the Brewster's angle at this boundary for each material. Okay, the material index of refraction are not given. We don't even know what kind of material that is. So what we can do is we can compare equation, because the word here has mentioned critical angle as well as Brewster's angle. So write down the two equations. For critical angle, sine theta c is equivalent to n2 over n1. Whereas for Brewster's angle, tangent theta p is equals to n2 over n1 also. You can see that these two has similarity, which is n2 over n1. So sine theta c is equals to n2 over n1. Tangent theta P also equivalent to N2 over N1. So you can simplify this equation by putting in the values there. Critical angle is already given here, which is 55 degrees. So sine theta C is equals to tangent theta P. I'll put in my critical angle here so that I can find my theta. Therefore, 1.52 divided by 1. Don't forget your shift tangent. You will get 56.7 degrees. So your answer should be D. Let's go to the next step of polarization, the third one, which is polarization by double refraction. Now, polarization by double refraction is easily confused with polarization by reflection because it's pretty much the same thing, like passing through different medium. But for polarization by double refraction, usually it applies to crystalline structure. For crystalline structure, the index of refraction is different depending on where the light hits. So such material are characterized by two indices of refraction, or they can also be called double refracting or birefringent material. So let's look at an example of crystalline structure here. We have calcite, or you are familiar with calcium. So calcite is actually a crystalline material. So once an unpolarized light goes into the calcite, it will break into two rays. Because why? There is index of refraction of NO, position of NO here. Also, there's index of refraction of NE. Index of refraction NE that varies with the direction of the propagation, depending on the direction of propagation. So there's two direction here. Direction it goes towards the E ray, and we have O ray. So both E ray and O ray would have different index of refraction. So we call that birefringent refraction or birefringent material. Okay. So ordinary ray is characterized by index of refraction of NO. This is the same in all directions. Whereas the secondary ray is the extraordinary E ray, which travels at different speed in different direction. This is characterized by an index of refraction of NE that varies with the direction of propagation. Okay, so that's the difference between polarization by refraction and by double refraction. Okay. Now, the last one, last but not least, we have polarization by scattering. This will be the easiest one for me because it's what you see in your everyday life. I'm sure you are very familiar with our blue sky. When it's not raining, when the sky is clear, there's no cloud around, you can see how blue the sky is. But you notice that when the sun goes down or when it goes up, the sky turns to red. Or at night, the sky is pitch black. So how does this happen? This is actually caused by polarization by scattering. Okay, so when light is incident on any material, the electrons in the material can absorb and re-radiate part of the light. This process is called scattering. So how does this work? Okay, in air we have our oxygen, we have our nitrogen and other particles. So this particle acts as the polarizer. Light will pass through them and it will be polarized. So I give you an easy example. Okay, the scattering of sunlight reaching observer on Earth. Okay, depending on where you stand or where you view the light from, is actually different. Why? Okay, let's look at this example. From the sun, we have the full direction of light, or we call that unpolarized sunlight. And then the light will hit a particle or a molecule. Let's say it hits an O2 or an N2 molecule. What happened is, okay, the horizontal part of the electric field vector instead of it causes the charge to vibrate horizontally. Okay, you see that it vibrates horizontally. Alright. The vertical part of the vector simultaneously causes them to vibrate vertically. So another one vibrates vertically. But observer is looking straight up, so he will only see light that is completely polarized in the horizontal direction. Because why? The O2 has blocked the vertical light, leaving only the horizontal light on the observer's eye. That's how you see the difference in color in the sky. So that's why the sun looks quite reddish at dawn or dusk, and the sky is a bit bluish. Okay, but specifically, how does this happen? We know that our light is actually a combination of 7 colors. So the shortest wavelength will be violet, whereas the longest wavelength will be the red color. So when the sunlight is scattered by gas molecules in the air, we know we have many gas molecules in the air now, and the sunlight will go all over and be scattered by the gas molecules. Violet is actually scattered more intensely than the red. So basically, because it has shorter wavelength, it is scattered more intensely than red. So when it's scattered more intensely than red, you would actually see more violet wavelength. But unfortunately, our eyes are actually more sensitive to blue. So you see blue instead of violet. The actual color that is scattered there is actually violet. Now it's different during sunrise or sunset. The blue will go away. So there will be more red, leaving all the red end of the spectrum. Hence the red color during sunset or sunrise. Okay. So you can see a clear picture here of the phenomenon. If you have the time, go through YouTube or go through books or anything else or even everything around you and relate it to this chapter. Actually, PHY260 it should be easy for you to score because you can actually relate it to your everyday life. It's what we've been using or we've been going through our whole life. Okay, so this will mark the end of our chapter 5, also the end of this semester for PHY260. I would like to thank you for cooperating during ODL. I know it's a bit hard for you guys, my dear students. I am so proud of you. We are so proud of you. So we would also like to apologize for our shortcomings. Unfortunately, this is definitely not the same as teaching you in class, and we've made quite a lot of mistakes, and with the pronunciation and everything, it is hard for us too. So let us go through this together. I'm sure you get good results, and we wish you good luck for your final test, and hopefully all of you will get A. Okay, so take care, stay safe and be healthy. Thank you and goodbye.